Okay, Newton was the first one to explain tides, and here's the thing. Okay, see the tides. Here's the moon, and this bulge is easy to explain. I mean, it's intuitively clear. This is closer to the moon, and so this the moon's gravity is pulling on this side of the ocean, and you got a bulge here. Why is the bulge over here? Okay, so Mr. Newton is the one who explained this. Okay, and here's so we'll quickly do this. Okay, so let me start off by saying, if now, I mean, in a sense, it's sort of a redundant statement, but if this was a point object, okay, it doesn't matter what this object is. If this was a point object, then of course you wouldn't have tides. Okay, you will only have tides if there's a differential force on either end. Okay, and that's what matters. How? So the force on this piece is stronger than this piece, than the force on this piece. And the greater the difference, the higher the tides. Yeah. So for instance, the sun exerts a gravitational force that is about 200 times greater than the force exerted by the moon. But the differential force is not as great as the force exerted by the moon. So that's why the moon is the one that really causes the tides. Okay. So again, that was a whole bunch of words. So let's see how the tides arise. Okay, again, the moon is the one that causes the most of the tides on Earth. Okay, so let's say here's the Earth and here's the ocean. What we want to do is explain this bulge, these two bulges. Okay. Now what we'll do is so the force of gravity, the magnitude of the force is given by, okay. So this would be the mass of the moon, and let's calculate the force per pound. Okay, and smaller the r is, greater the force. Okay, so let's say we'll just make up some numbers. So the gravitational force of the moon on a pound of Earth here, let's call it is 100 units. Okay, I'm just making up some number. What will be the gravitational force per pound of a pound here? Will it be greater than 100 or less than 100? Greater, so we'll call it 102 pounds. How about here? Greater than 100 or less than 100? Less. Let's call it 98 pounds. This one will roughly be 100 pounds as well, 100, except that it is directed towards the center of the moon. Or we'll call it, okay, so actually we'll call it, all right, we'll call it 100. Okay. Now let's do the following. So this has a component like that, and that component is really 100. It has a small component. And now let's say 100 is 0. We're resetting our scale. 100 is equal to 0. So now the net forces are, so this will be 2 pounds in this direction. This will be 100 is 0, so since this was 98, there's a net force of 2 pounds in this direction. £2 pounds in this direction, and there's a net force like that and little force like this. And you see, so this 2 pounds will give you that bulge, this 2 pound will give you this bulge, this component will make the tide go down a little. So when the moon is here, if you're here, you have low tide, and if you're here, you have high tide. And if you're here, you have high tide. Okay? So again, this bulge really came about because the Earth was being pulled away from this ocean. Again. And that's what Mr. Newton gave us. All right, so what matters is this difference, 102. So the difference in force was between this portion and this portion was 4 pounds. And that is what gives you tides. Okay? The sun has a stronger force, except that the difference in force between this point and this point from the sun is not 4 pounds, it's 1 pound. Why is the difference so small for the gravitational force from the sun? It's so far away, and then this difference is small compared to this distance. This difference is large compared to this distance. Okay, so that's why the moon gives you the tide. Okay.
So can planets, I know there's no water on the sun, but can planets somehow do some kind of tide with the sun if they're close enough?
I'm sorry?
Can planets, when they circle
Mm-hmm.
the sun, can they kind of do the same pulling force?
Yeah, in fact, so good question. Here is the moon. In fact, the Earth bulges as well, slightly. What happens when the moon goes over here?
The bulge will shift.
So this bulge has to relax back. It's like you pull the Earth. That has to relax back, and it has to bulge this way. It's like you stretch the spring, Earth is solid, and as it goes back, relaxes back, that energy gets converted to heat. So mechanical energy is being converted to heat. Where is that energy coming from? The Earth is slowing down, the spin is slowing down. The Earth used to, when it was first formed, it used to spin once in 9 hours. Okay? And now it's spinning in 24 hours. So you guys are actually getting 3 times the time for doing homework than if you were here 5 billion years ago. Yeah.
Is that where tectonic plates come from?
I'm sorry?
Is that where tectonic plates come from?
No.
No?
Yeah. So this is the actual, Earth bulge. Okay. So tectonic plates are okay, what is the radius of the Earth? 4,000 miles. The tectonic plates are, so the top 40 miles, so that's 1%. This is broken up into shells. And this layer underneath it, right below it, because of the weight of all this guy, this is plastic. It's sort of a liquidy surface. So you can think of the plates as, pieces of wood floating on honey. Yeah. And then as heat rises, the convective currents will make the plates move. Yeah. And they move each plate moves about 2 inches a year. So they're moving in all kinds of directions. Okay, so Mr. Newton, so this is the tidal force per unit. What this is telling you is, okay, so here's the object, and what is the difference in force between these two ends? So F1 minus F2 per pound, so force per pound that is the tidal force. Tidal force per unit mass. Okay, so the moon exerting the tidal force on Earth, there it is, 1 times 10 to the minus 6 Newton per kg. And the sun exerting the tidal force on that, you see, is half the tidal force on the Earth. It's 0.5 times 10 to the minus 6. Okay, so the tidal force of the sun is half that of the moon. Okay. So the moon is what's responsible for half of our, so 2/3 of our tides. Okay. So when the sun and the moon are lined up, then you have the tides are high or stronger. And these two configurations are the same, and they're called spring tides. When the moon and the sun are lined up like this, then they're working against each other, and these tides are not as high. Okay, so these are neap tides. The tidal forces can rip stuff, so most stars are binary stars. We happen to be unlucky, we have only a single star. But so if this star expands, and it happens over life cycles of stars, they'll expand, and then stuff can get ripped up from here. Okay. And if this is at the threshold of, if it can go supernova by getting a little mass, that's how some of the stars go supernova. Okay, Mr. Newton gave us the magnitude of the force between these two objects was Gmm by r squared, and something like in 1687 or something like that. Okay, and the next improvement to this law was given by Einstein in 1916. Okay, so about 250 years later. And that's the general theory of relativity. You know? And there's his equation. Okay, so we graduated from here to here. Took us 250 years. Okay. And what this equation tells you is, this tells you this is related to how space-time is curved. See this curvature? How space-time is curved. And this term is related to the matter distribution, or matter and energy distribution. Okay? So what this equation is telling you is, matter and energy tell space-time how to curve. Okay? So you see the sun has curved this space-time, and the earth is just going. So if there's no force acting on an object, what is the trajectory of the object? So let's say if I take a baseball and throw it out in space, it goes in a straight line. Okay? What is a straight line? It's the shortest distance between 2 points. Okay? And so the shortest distance between 2 points in Euclidean space is given by, so in flat space it's given like that. That's how you calculate distances. Okay, so in space-time, this fellow allows you to calculate distances. Okay, I'm going to write down the formula, but don't worry about it. So distance between 2 points is given by, this is space-time coordinates. Okay, here's how you calculate the distance. Again, don't worry about it. It's exactly like this formula, you see. And these go over four values, 0, 1, 2, 3, and 1, 2, 3. 0 is time coordinate, and 1, 2, 3 are spatial coordinates. Anyway, this is how you measure distances. All right, so here's what Mr. Einstein is saying. See, matter tells space-time how to curve, Matter and energy tell how space-time how to curve. And small pieces of matter that do not distort the space-time, they go from point A to point B in the shortest distance. So they are going in straight lines, except that this is how you calculate the shortest distance between 2 points. Okay? So what we think of as curves are straight lines in curved space-times. Okay? Those are called geodesics. Okay? So space-time is influenced by matter and energy, and matter and energy tells space-time how to curve. Space-time tells matter and energy how to move. Okay, so the curved space-time tells matter how to move, and all matter is moving in straight lines. Okay, so and those are called travel along straight lines called geodesics. So, okay. And like we said, what is a black hole? So let's say here's an object. If you squeeze the object within a radius such that the escape velocity is c, the speed of light, this is called the Schwarzschild radius. So if you took this object and squeezed it within this radius, then the object will become a black hole. Now, once you squeeze it past this radius, there's no stopping. That matter will collapse to a point, a central point. Okay, if you wanted to make our sun into a black hole, you would have to squeeze it to a radius of 3 kilometers. 3 kilometers is roughly from here to Beach Street. Okay, so if you could squeeze our sun from here to actually the river within that radius, then you could turn it into a black hole. Yep.
So, is the reason light's affected by gravity due to the bending of space-time, since light's massless and it can't be influenced by gravity?
So here's the space-time tells matter and energy. A photon has energy. Okay. So here's your. So in fact, Einstein told us that. So this bends space-time around it, and light will bend. Okay. So here's light coming. So this arrow should be the other way. Light from the star is being bent by the gravity of the sun and reaching us. Okay, just 1 second. So this was one of the first things that was experimentally tested from Einstein, after Einstein gave us theory. Okay, so here's the deal. So this star is there. Okay. And when the sun was there, its light got bent. And what are you hardwired? Your brain is hardwired to think that light travels in a straight line. And you see this image of the star over there. Okay. Are there stars in the sky right now? Can you see them? No. Why? The light of the sun is swamping that starlight. Okay? It's like you're a billionaire and you noticed a penny lying on the road. That doesn't happen. Okay? All right, so how do we measure this? How would you even measure this?
Could you do it at sunset and you can see some stars?
You wait for a solar eclipse. Just block off the sunlight. So people were chomping at the bits for the first solar eclipse after Einstein came up with this theory. Okay. All right, so here's the deal. So here's the sky. here the position of this star, and this is the position of the star in a background of stars. Okay, so we know the position of the star, and then when the sun was here, this was night. You map this position of the star, and when the sun came here 6 months later, now you're measuring. So here's the star amongst all these guys, and now when the sun came here, now the position of the star is appearing there. Okay, you measure the position of the star, now it's appearing next to these guys during solar eclipse. And so you could measure amount of bending of the light. And that was exactly equal to what Einstein had predicted. Okay. And Einstein was on the cover of the New York Times. Yes, my friend?
I don't understand why doesn't the sun's gravity just keep pulling Earth towards it? Like, what's stopping it?
It is pulling towards it. It's all right. That thing was falling, right? Okay. It was still falling, but the faster I threw it, the curvature was smaller and smaller. If I threw it at 8 kilometers a second, the curvature will match exactly the curvature of the Earth. If I throw it at 11 kilometers a second, it will just go. So that's what's happening with the sun and the Earth. It's going at 30 kilometers a second. Here's the sun, here's the Earth. At 30 kilometers a second, this is falling towards the Earth, except that, it's falling towards the sun, except that see, if it went straight, it would go like that. See, it's falling towards the sun. Okay, but the rate of fall is such that it never gets closer to the sun. So that's what's happening. Yep. So, in fact, if the sun wasn't there, it would just go straight. Okay. All right. So this is, you saw that there's a central black hole, and these are stars going at crazy speeds around this black hole. They're going half the speed of light, and so amazingly fast. Yeah. So at the center of many galaxies, you have black holes whose masses are like billions of solar masses. You guys have heard of gravitational lensing? What does a lens do? It forms images and stuff like that. So again, so this, so here's the deal. Okay, so here's a picture of two objects. You can see that there are two objects, right? That and that. You can go at night and go see this. They're the same object. How do we know they're the same object? Okay, so what you do is you measure the intensity of light with wavelength. This is called a spectrum. Okay, so let's say it looks like this. Now I'm doing a simplified picture. Okay. You do that thing for this thing, and it's exactly the same. It's very unlikely that two different objects would have that. So it's the same object. So what's going on? All right, here's what's going on. So here we are on Earth. Here's a galaxy between us. So the galaxy is somewhere here we are, and there's that object further out. A quasar is an extremely bright object. Okay, so it's believed it's a massive black hole eating up stuff, and that's how it's very bright. As the stuff is falling into the black hole, it heats up tremendously, and it's emitting all that light. All right, anyway, it's a bright object, and this is one of the furthest objects we can see. You know, the further out you are, you'd better be bright for you to be able to see. You know? So this light is coming over and is bent like that, and there's the image of that object. This light is coming over here and bent like that, and there's the image. So for the same object, we're seeing two images because of this intervening object. So if this object was not there, we'll just see one object, one quasar. Okay? So this is gravitational lensing. Okay? And this happens quite often. See, these two are the same objects. All these are the same objects. And so you can calculate, so here's the Earth and all these objects. You're seeing multiple images of these objects, and so you can calculate the stuff, intervening stuff that is doing the gravitational lensing. And all this blue stuff is the intervening stuff. Now the deal with this blue stuff is, I mean, that's computer generated. It's not blue. It doesn't emit light. This thing doesn't emit light. It's not absorbing light or emitting light. It's not interacting electromagnetically, and so it's called dark matter. Okay, we don't know its nature. So right now the composition of the universe is 70% dark energy, 25% dark matter, and 5% normal matter. All right. You see, 95% of the universe, we don't know its nature.
Are dark energy and dark matter like known to be related, or are they just called dark because they're confusing?
Not because they're confusing, because we don't know about them. Then they're not related. Yeah. All right, guys. I'm tired. We'll stop. Okay. Unless you absolutely had to hear about gravitational waves. I can tell you in 30 seconds about them.
I want to ask, whenever I see like space time, it's shown like as a flat paper, but like we obviously live in 3D space. What is that trying to represent?
I'm sorry?
Whenever I see space time, it's like flat, this, and it's like round. But obviously we live in 3D space. So what is that like actually representing? It's not like following me through obviously this paper. You know what I mean?
All right, so okay, so here's one point x1, x2. Oh. Here's another point x2, y2, z2. And the distance between these 2 points is given by x2 minus x1 square plus y2. Okay, and this is Euclidean geometry. You studied this. That's the distance between these 2 points. Okay. When Einstein came along, he said, you can't measure time and space coordinates separately. They have to be measured together. Okay? Yeah. So, and the distance between these formulas, if there is no matter in the universe, then space-time would be flat. And the way you would measure the distance between these 2 points would be c squared t2 minus t1 square minus x2 minus x1 square minus y2 minus y1 square. Very similar to the formula that you saw for Euclidean geometry. This is called Minkowski space. This is a flat space-time. Okay? Now, as soon as you go buy a star from a store and put it in the space-time, it curves the star, the space-time like that. And this formula changes to c. This formula changes to that term, this matrix. Okay, so the way you, okay, let me make sure. So that matrix is 1 0 0 0 0 minus 1 0 0 0 0. This is this formula. Okay, that's a flat space-time. And when you go buy a star and put it in here, this matrix changes, and this becomes, again, simplifying this, it's actually that matrix, a row matrix, dy dz. So and this matrix becomes G00, G01, G02, G03, and each of those guys are functions of the coordinate. Okay. And so on. So each of these guys become functions of space-time coordinate, and that's how you calculate the distance. Okay, and so the distance formula changes. Okay, and that's what I wrote over there earlier. Okay. So when you bought the star, what you did is you changed this matrix from here to here, and this change tells you how this space-time curve. That's what happened. Okay. All right, let's go back to gravitational waves. This is an absolutely amazing story. Okay. I mean, I can't tell you how amazing it is. I mean, the more you think about it, the all right, so if you want to emit an electromagnetic wave, what you need is a charged particle, and you need to make it accelerate. Okay, so grab hold of a proton and oscillate, make it oscillate like this, then it's accelerating. And if it's accelerating, then it'll emit electromagnetic waves. Okay. So when this object accelerates, it emits electromagnetic waves. You want to emit gravitational waves, what you need to do is grab hold of any mass and make it accelerate. And you just saw how to make a mass accelerate. You just jiggle it back and forth. Okay? So if I just jiggle my hands back and forth like that, I'm emitting gravitational waves. Except that the waves are so weak, there's no way in hell you'll be able to detect it. If you want to have any hopes of detecting this, you'd better have a massive object and detect it. What do you mean by a massive object? An SUV? No. I'm sorry? A big star. A black hole, a big black hole. I mean, if you take a big star, it's more than likely to become a black hole. How do you make a black hole jiggle? Nobody's going to grab it and make it jiggle. You recruit another black hole. This black hole, they go around each other, and so this is essentially jiggling. Okay? And they will emit gravitational waves. And we can potentially detect them. All right, I will tell you, oops, so let's see what is it that we really detected. Oh, that wasn't smart. I should have cleared it before duplicating it, but anyway. All right, so the first thing we detected was, so here are these two black holes. This was 35 solar masses and 32 solar masses or something like that. 67. Don't worry, yeah, something like that. So these two black holes had been going around each other for billions of years, or many millions of years. This pair was 1.3 billion light years away. Okay. Now, as they're going around each other, they're losing energy and they're coming closer, and then they're going faster and faster. Okay. And the faster they're going, they're accelerating more and more faster, and the acceleration is greater, and they're emitting more and more energy. So this was going on for several billion years. We detected them, so they came close enough and they eventually merged. We were able to detect the energy in the last 0.2 seconds. 0.2 seconds. That is equal to 200 milliseconds. So 200 milliseconds before they died, they were emitting so much energy that we were able to detect that. Well, how much energy was this? This was about, do you know how many stars there are in the universe? There's about 10 to the 24 stars in the universe. A trillion stars. You see how much energy the sun emits. Okay? So all the energy, the power that all these stars are radiating in the last 200 milliseconds, this was about 100 times all the stars that were radiated. And we were barely able to detect it. So if your eyes could see these gravitational waves, the energy that was reaching you was 100 times more than the energy than all the stars were emitting. All right, let me give you another perspective. So these two combined, so this is 67 solar masses. They started off with 67 solar masses, and they ended up with, the merged black hole had 64 solar masses. So 3 solar masses of energy was radiated away, and mostly in the last few seconds. To put that in perspective, our sun, over 10 billion years, loses about 1 to 2% of its mass. Okay. Like I said, I can keep telling you about this stuff, and your head will spin and spin. Okay. So here's the signal. See, this is the signal from 0.25 seconds to 0.45 seconds. This is when the two black holes merged. Okay? So that's 200 milliseconds of data. And this waveform matched exactly what Mr. Einstein predicts. Okay. So here's what was going on. So here are two black holes going around each other. That's the size of their radius in the last 200 milliseconds. The one was a 36 solar mass, and the other was a 29 solar masses, so 65 solar masses, and then the merged black hole had a mass of 62 solar masses, so 3 solar masses were radiated away. The power was 50 times that of all the stars in the observable universe in that last 200 milliseconds. Okay, so how do you detect these gravitational waves? Okay. So imagine this. It's a powerful event. So much energy is being radiated, and we've been trying to detect these gravitational waves for the past 60, 70 years. And we just detected them about 10 years ago. So how do you detect them? All right, so here's the deal. If a gravitational wave goes by, okay, so you just arrange a bunch of marbles like that. What it does is gravitational waves, it distorts space-time. So what it'll do is it'll distort the space-time, it'll distort the space and such that, okay, for a quarter cycle it becomes like this. These marbles will look like that. And then they'll look like this and then like that, okay? So that's how they'll distort. It's actually, so think of space-time as a rubber sheet. It's actually, as the gravitational wave goes by, it's stretching the rubber sheet like that. Well, so how do you detect the stretch? Because the stretch, let me give you the number, 1 meter. Okay, so if the radius of this thing is 1 meter, then it stretches to 1 meter plus 10 to the minus 21 meters. To put it in perspective, the size of an atom is 10 to the minus 10 meters. The size of a nucleus is 10 to the minus 15 meters. So the stretch is that much. It is like stretching the Earth-Sun distance by an atom. And you have to detect that. Okay, so let me state that again. If the distance between the Earth and the Sun, what is the distance between the Earth and the Sun? I'm sorry? No, that's the radius of the Earth. Earth-Sun distance is 92 million miles. That stretches by an atom. You have to detect that. Unbelievable. You guys understand that? All right, so how do we do that? Okay, so here's how you do it. You take a beam of light. This is a beam splitter. Okay? And this half the beam goes there and comes back through like that. Half the beam goes through like that and comes back like this. What you can do is you can move the mirrors such that these two beams cancel each other. If one beam comes like this, you make the other beam come like that. And you see they're canceling each other. Okay? This peak is canceling that peak. And that depends on the distance they have traveled. So you make sure that they cancel each other exactly. And then you wait for gravitational waves to pass you. When a gravitational wave passes you, if now this distance, see this got stretched, so this light beam is traveling a greater distance, and now they're not matching each other. They're not canceling exactly. So as soon as you see some light, a gravitational wave passed you. Okay. And then, the next quarter cycle, you'll see more light. Okay, so that's what was measured. So the intensity of light in the photodetector is what was measured. That's what the signal is. Okay, that's the intensity of light in the photodetector. The only problem is, okay, a truck drives by, it'll disturb this distance and you'll get light in the photodetector. So how do you make sure it's not a truck and a gravitational wave? What?
Put it in space?
I'm sorry?
You put it in space?
Yeah, no, but this was detected on Earth. So what you did was, so you had a multi-billion dollar lab here. You have another multi-billion dollar lab over there. So if the gravitational wave came by here and it gave you the exact same signal there, then it was a gravitational wave and not a truck. Okay. Now we have detectors all over the world. Okay. So we can detect all kinds of gravitational waves.